Hi everyone, it's Ellie from The Curious Geographer and welcome to our live interview. Good to be back with you all, and we've got a really interesting interview with Professor Chris Stokes, and it's going to link, if you do A-level geography, links to so many different parts of the specification. So whether you study water and carbon, you might have learnt it with globalization when you look at Antarctica, or also if you obviously study glaciers at GCSE or A level. So we'll kind of talk about some things, and if you have some questions, please just put them in the chat and we'll try and get to them as well. So yeah, as I said, today we are joined by Professor Chris Stokes, who's a professor in the Department of Geography at Durham University. Chris's research focuses on glaciers, lots of different scales, and so might be the monitoring of small mountain glaciers over the last few decades, or large-scale reconstructions of ice sheets over tens of thousands of years. Chris uses GIS and remote sensing to monitor changes in glaciers, and in particular has done some research on Antarctica, which we'll talk about, particularly East Antarctica and supraglacial lakes, which we'll talk about. So if I pass over to Chris, so Professor Chris Stokes, if you wouldn't mind introducing yourself a bit and letting us know what your research interest is and a bit about your current role.
Thanks, Ellie. That's great. It's lovely to be here this afternoon. I think you've done a great introduction, actually. I don't have too much more to add, but yeah, I guess I'm a glaciologist. That's somebody who studies glaciers, and most of my research is looking at how glaciers respond to climate change. And as you said, a particular theme at the moment is looking at how modern day glaciers are responding to global warming. But actually, I've also done research on, the last ice age and how quickly glaciers and ice sheets retreated into and out of ice age cycles. I'm also interested actually in how glaciers, when they move over the landscape, create landforms and deposits. I'm particularly interested in drumlins, which I know some people will have heard of. But yeah, at the moment, most of my research is aimed at looking at how modern day glaciers are retreating and shrinking and losing mass in response to what we would like, what we call global warming or anthropogenically forced climate change.
Hi everyone, I've just lost Chris really quickly, so if you can just bear with me, and I'll call him back because we've got some really interesting things to talk about. So I'm just going to pause this, take off my thing for a minute, and put back on the welcome screen, but I'm just going to give him a quick call. My Skype just seems, I think it's my Skype, it just seems to have frozen, which is really bad, but we'll edit this out later. But yeah, if you could just be patient, and if you do have any questions about glaciers, if you just want to let me know, that would be, do you want to just ask me about them, that'd be fantastic. Hi everyone, we're back again. Thank you for being super patient. Chris, you were just telling us about your current research, and I think you might be about to tell us maybe where you might have been on some field trips as well. So I'll pass back over to you.
Yeah, so I was, I'm not sure which bit it cut out, but yeah, most of my research at the moment is looking at how glaciers respond to climate change. And I was saying that I'm interested in both small mountain glaciers in mountain ranges around the world, but also in glaciers in the Arctic and the Antarctic as well. And that's where I do my research. Clearly, I work in the Geography Department of Durham, and I teach on modules, particularly modules related to glaciers and glaciation. And I also teach a module that takes an integrated look at the Arctic as well. So from a kind of human and physical perspective, which I teach with a professor in human geography, which is really good fun and has a field trip to the Arctic as well. So yeah, that's what I do. Okay, well, that's a great question. And in short, they melt. That hopefully comes as too much of a surprise that when we increase temperatures around the world, that glaciers will start to melt. And as geographers, I think it's really important to think about how this plays out at different scales. So I think hopefully you're going to show a slide at the moment, which is actually from that field trip to the Arctic. So this is just a typical glacier that we take students to in the very far north of northern Norway. And this is a glacier that we visit every year. And that photograph is showing you where that marker post, that silver marker post at the front of the photograph is showing you where the glacier was back in just a few years ago, 2010. And this is showing you the kind of retreats. That's several hundred meters of retreat just in the last 10 years or so. So clearly, glaciers are melting. And you can see just in that photograph what kind of impact that's having on the environment. It's not just that the glacier is melting, we're seeing it thinning, we're seeing it retreating, and we're seeing a lake starting to form in front of it as well. So clearly in a warming climate, glaciers melt. And we're seeing this across the world. There's very few areas of the world now where glaciers are not retreating. We're actually seeing glaciers disappearing as well. And I think we've got an illustration. And the irony is not lost on me. This is called Glacier National Park in Montana in the USA. So, this is a national reserve, if you like, where glaciers have been for hundreds of years, and we're seeing them disappear. There's a couple of images there of the same glacier, Shepherd Glacier in 1913, and then again in 2005. And this is a glacier that's pretty much disappeared. And that's, again, being seen around the world. We could go to several continents where we know there were glaciers and they're disappearing. There was a really well-publicized event you can probably find very easily on the web, showing where somebody held a funeral for a glacier that had kind of disappeared in Iceland. So this is a pattern that we're seeing around the world, and we're not seeing many glaciers advancing at all. And the one or two that are advancing, there's often a very good reason for it. That's reasonably well to explain. So if I just come back then to something I said a few seconds ago about what are the impacts of this. And as a geographer, and hopefully as geographers listening in, we like to think of things at different scales. And I'm going to break down the impacts of glacier melt at 3 scales. First of all, there's the global impact. And the global impact of all of these small glaciers retreating is that we're seeing sea level rise. So one of the main impacts that will be felt around the world from glacier melt is sea level rise, and it's currently rising at just over 3 millimeters per year. So that's going to be felt not by the people who live nearby the glaciers, but it's going to be felt by people who live in the low-lying coastal zone. 680 million people live in what we call the low-lying coastal zone, and they're going to be impacted by this global impact of melt, which is sea level rise. And then we can come down to the next scale, which I tend to refer to as the regional scale. And regionally, there are large parts of the world's population that rely on glacial meltwater for domestic use, for irrigation of crops, for hydropower. It's been estimated that about 1/3 of the world's population somehow interacts with glacial meltwater at some point. So huge numbers of people are going to be affected if these glaciers start disappearing, if they start to melt more rapidly. We might see a short-term increase in river flow from glacier melt, but then a much longer-term decrease in terms of water resource available from glacier melt. So I'm thinking of places like Central Asia, tropical South America, where we have glaciers that provide a very reliable source of water that's going to be interrupted over the next few decades and few hundreds of years. That's the regional scale impact of glacier melt. And then thirdly, finally, we're starting to see hints that glacier melt and retreat in high mountains might start to increase the risk of geohazards. So there was a really well publicized event a few weeks ago in the Himalayas where a glacial lake outburst it broke through a dam, it caused a flooding event, which unfortunately led to loss of life, damage to infrastructure. Now, there's a little bit more uncertainty about this, but certainly there's a growing body of evidence now that as we retreat glaciers in high mountains, we start to destabilize slopes, we start to grow lakes that are unstable, and it increases the risk of geohazards. So in answer to that question, the main impact is glacier melt and retreat, but then there are three main impacts at the global scale, the regional scale, and at the local scale.
Brilliant. So that question before for everybody, just to check, was what was the impacts from climate change? And I really like how you talked about the different scales. So at A-level geography, we're constantly trying to talk about that kind of global, national and local scale. And just to recap, how many percentage of people did you say around the world potentially going to be impacted from glacial melts?
Yeah, so I mean, it depends. If you think of the first one, the global sea level rise, around about 680 million people live within a metre or so of sea level. And we might come back to that when we show an illustration later of some future projections of what sea level rise is. So that they're going to be impacted by sea level rise because it's going to be, obviously leading to sea level rise in coastal areas. But I talked about water resource use, and it's been estimated that about a third of the world's population will interact in some way with glacial meltwater. So I'm thinking particularly of the big rivers in, say, Central Asia, the Brahmaputra, the Ganges. All of these are fed by glacial meltwater from the Himalaya, and that's really important. Tropical South America is another area where they use a lot of the glacial meltwater for irrigation, for domestic use, etc., etc. So, there's quite, it's not something that we're always familiar with in the UK. Certainly in other countries, I mean, Norway we've mentioned, uses a large amount of glacial meltwater for hydropower, which is going to change over the future as glaciers shrink.
Brilliant.
I think we've got a video as well just to show you some of these processes playing out because, it's very easy to look at these static photographs, but I think Ellie's going to play a video now of Solheimjökull, a glacier in Iceland, and what you're seeing on this video is what happens to a glacier, and hopefully this time-lapse footage is speeded up over a few years of what's happening to this particular glacier, and you should be able to see that the glacier is ever so slowly moving forward towards you, but it's also retreating more rapidly. So glaciers flow, that's one of their defining characteristics. They are kind of slowly creeping forward, but clearly the impacts of climate change on this particular glacier mean that it's actually retreating much more rapidly than it can flow forward. You're seeing the glacier thin, you're seeing it retreat, and you're seeing a big lake form in that proglacial zone. And in Iceland, it's probably not going to have a huge implications for the local population, but we know, even in Iceland, that we're seeing some of these lakes grow. And sometimes the lakes under the ice actually burst and they wash away bridges and they knock away a road for a few weeks that has to be rebuilt. So that's just a real life kind of example, and hopefully you see the dynamism of glacier change in this particular location in Iceland. And I'd really encourage anybody watching to go and have a look at that Extreme Ice Survey website, where there are actually a number of examples of this glacier retreat in different parts of the world.
And we showed the video as well for them to see. So just to remind, if there are any questions about this, I mean, you've already said so much, which we could ask loads of questions, but we do already have some planned out. But if anybody wants to write them in the chat. I think also one thing that's quite difficult sometimes with students is that glaciers, you don't see them in our day-to-day lives. So it's quite hard to maybe actually understand what impacts might have from glacial change. I know from teaching it, it's sometimes quite abstract ideas. So what are the differences between the Arctic and Antarctica?
Okay, yeah. So again, put simply, and it is quite simple in that if we think about the Arctic is mostly ocean surrounded by continents, and that ocean freezes over every winter. and every summer it contracts. But of course, we do have quite a lot of glaciers in the Arctic, in the Canadian Arctic, in places like Svalbard, in the Russian high Arctic. There's a large amount of what we call valley glaciers and ice caps in the Arctic. And we have a very big ice sheet in the Arctic, the Greenland ice sheet. And the Greenland ice sheet locks up about 7 meters of equivalent volume of sea level. So if we lost the Greenland ice sheet overnight, sea level would increase by about 7 meters. So when we're thinking about the Arctic, we're particularly concerned because the Arctic is one of the most rapidly warming places on Earth. And as a result, Arctic glaciers are melting more rapidly in some cases than glaciers elsewhere around the world. And we're very worried about that. If we think about the Antarctic, well, that's much further away. I think we've got a slide actually just to illustrate what is happening in Greenland, because it is one of the things that we're really worried about. And because Greenland doesn't sit over the North Pole, it actually sits a little bit further south, almost in a kind of mid-latitude position. And Greenland's a bit of a puzzle. I mean, in some ways, Greenland shouldn't really be there. It's this huge ice sheet that perhaps shouldn't even be there. But Greenland's getting attacked from above and below. And by that, I mean that temperatures in the Arctic are warming, and that's causing increased melt, what we call surface melt. Okay, and you can see that it's leading to lakes forming, it's thinning the ice sheet from the top down. The other thing we've observed in Greenland is that there have been some changes in the access of warm ocean currents underneath the Greenland ice sheet. So we're seeing these warm ocean currents, I think they're depicted in red on that illustration. Warm water is coming in at depth, and then it's actually eroding and melting the underside of the floating bits of Greenland as well. And so Greenland is being attacked from both surface air temperatures, but also from warm ocean currents. And you asked me what the difference are between the Arctic and the Antarctic. Well, if we move to the Antarctic, then most of the world's ice is stored there. So the Antarctic ice sheet actually holds about 58 meters of sea level equivalent. So by far the vast majority of the Earth's ice is in Antarctica. Now the good news, at least for the moment, is that the Antarctic is not warming as much as the Arctic. So at the moment, the Greenland ice sheet is melting a lot, Arctic glaciers are melting a lot in Iceland, in Svalbard, in the Canadian Arctic, in Russia. In the Antarctic, we're not seeing so much of the ice melting from the surface. But we are worried in Antarctica about, in particular, the western Antarctic ice sheet. Okay, it's a little bit of Antarctica that we know is being exposed to warmer ocean currents, and that is contributing to sea level rise at the moment. It's losing mass because that same process we see in Greenland, that's warm ocean currents coming in under the floating portions, thinning them. And as you thin the floating portions, you're kind of weakening what we sometimes refer to as the buttressing effect. These floating portions act like doorstops, and when you thin them because of warm ocean currents, you remove that buttressing force, and then the ice flows more rapidly into the ocean. So I guess the big difference between the Arctic and the Antarctic is in the Arctic, you're seeing glaciers melt from above, from air temperature increases, and from below, from warmer ocean currents. In the Antarctic, most of the mass loss that we're observing is actually only from warm ocean currents. There are some bits of Antarctica that are warming quite rapidly, but that's not where most of the glaciers are. It's West Antarctica in particular that we're worried about because we've got warm ocean currents coming in there.
Fantastic. Your research in particular has focused on Antarctica and recently East Antarctica. How is Antarctica impacted by climate change? I mean, you started to talk about like the warming seas as well. And you said there was a difference between East and West. So what are the impacts? How does that vary between East and West?
Yeah, I mean, this is something that we've been working on for around about a decade now, because most of the research in Antarctica has been focused on the West Antarctic ice sheet. This is an ice sheet that is sat on ground that is well below sea level, which makes it particularly vulnerable to ocean warming. The vast majority of ice in Antarctica is actually in the East Antarctic ice sheet, and the East Antarctic ice sheet has about 52 meters of sea level equivalents, but large parts of it are actually on land that are above sea level. And so the tradition, if you like, the paradigm has often been that East Antarctica is the more stable of the two portions of Antarctica. We've got the West Antarctic ice sheet, very, very vulnerable to ocean warming. We know it's losing mass. When we look at East Antarctica, we see an ice sheet that we think has been around for millions of years, or at least most of it has been around for millions of years. We think it's relatively stable. But our research group in Durham has just started to see some evidence that parts of East Antarctica might also be losing mass as well. And it might be losing mass because of the same processes that we've seen in West Antarctica, because of some parts of it, not all of it, but some parts of it are seeing increased flow of warm ocean currents under the ice sheet and eroding it. And we've also seen some evidence in East Antarctica of increased melting as well. I think we have a couple of slides actually to illustrate some of the differences between Greenland and Antarctica and glaciers. I think we've got a slide that we can show you that illustrates the sea level contribution from these different components of what we call the cryosphere. So if we look at the Greenland ice sheet there, you can see that there are some projections of what might happen by 2100. You've got some observations in the early 2000s and 1990s, and then you can see a kind of a pinky and orange swathe of colour takes you towards 2100, and then you've got a blue line. And those two scenarios are showing you different emission scenarios. And these are computer models trying to predict what might happen in Greenland. And you can see that, you know, a worst case scenario, if we look at the upper range for Greenland, we're looking at about 25 centimetres being added to sea level just from Greenland. A low end scenario would see about 5 centimetres, you know, 0.05 metres. And if we look at Antarctica, again, it's a very similar pattern. We've got high emission scenarios suggesting we could be looking at about 20 to 30 centimetres. Low emission scenarios, hopefully we can keep it to below maybe 5 to 10 centimetres. The glacier mass loss is actually a little bit less in terms of the contribution, maybe 10 to 20 centimetres by 2100. So the picture here, when we add all these uncertainties together, we're looking at a range of between 0.343 metres under a low emission scenario and maybe about 0.84 metres, so 84 centimetres under a much higher emission scenario. And this really, to me, illustrates the importance of trying to adhere to the Paris Agreement and limit warming to a low emission scenario. It really will make a difference in terms of sea level rise scenario. So I just wanted to make that point there. And then if we were able to just kind of skip forward to another slide, which shows a map of Antarctica, it hopefully will just illustrate in a bit more detail. What I've tried to do on this image here is show you the difference between the east and the west. You've got the West Antarctic ice sheet, which is about 5.3 meters of sea level equivalent if it were all to melt. And you've got the East Antarctic ice sheet at 52, just over 52 meters of sea level equivalent if it were all to melt. And you can see that that portion of West Antarctica, those deep blue colours over the western part of Antarctica on the right-hand side of the illustration are showing that most of the ice sheet is below sea level, making it very vulnerable to ocean warming and possibly even some kind of runaway retreat because of warm ocean currents. Whereas in East Antarctica, we've got whole mountain ranges and we've got the ice sat on these mountain ranges, relatively stable, hopefully largely immune to changes, but, and it's a big but, some catchments in East Antarctica are vulnerable to the ocean warming process. And they're the ones that you can see in blue there in the bottom right. And that we're starting to see some quite worrying signs from some of the satellite observations that we've taken over East Antarctica that dynamic changes might be occurring and it too might be losing mass.
Fantastic. And we did get the slide up to see the projections as well, so kind of modelling that. And we're going to talk to you a bit about using remote sensing, which we can see on those maps that you're using GIS to help model that. So we'll come to that in a sec. part of one thing that you have been looking at in East Antarctica is supraglacial lakes, tongue tie. What role do they play in ice sheet mass balance?
Yeah, so when ice sheets melt from above, they release meltwater, and sometimes that meltwater ponds. It produces, if you like, small puddles that grow into much bigger lakes during the summer melt season. And we have some case studies, if you like, from the Antarctic Peninsula. That little stretch of land that goes up towards South America is one of the places in Antarctica that's warming the most rapidly. And there's been some really nice observations using satellite images to show that when lots of these lakes form on the floating portions of the ice sheet, which is sometimes quite thin, the lakes get so big and heavy that they actually drain, they cause fractures in the ice that drains into the ice, and they can cause this rapid collapse of a floating ice shelf. And as temperatures have increased over the last few decades in the Antarctic Peninsula, almost one by one, we've seen these ice shelves collapse. We've seen lakes form on them and these ice shelves collapse. And one of the questions we've been pondering over the last few years in our research group is, where else in Antarctica are these lakes occurring? And nobody really knew the answer to that question until we could benefit from the large amounts of kind of satellite imagery that's now being generated. So we can get an image almost every 6-7 days from Antarctica now, where we can see the surface of the ice sheet and we can very quickly map lakes. And I think one of the slides there shows an example of all the different places that we found lakes have been observed in Antarctica. Now, there's not many in West Antarctica, but we discovered that there are 65,000 lakes turning up on East Antarctica. So this was the first study using satellite imagery to consistently observe the ice sheet surface, and we found far more lakes than we thought were there. So again, this is a little bit of emerging evidence that's questioning this paradigm that the East Antarctic ice sheet is stable and largely immune from changes. Instead, as I said a few minutes ago, we're seeing parts of that ice sheet melted by warm ocean currents, and now we've got some evidence that large numbers of lakes are forming, and they might be causing parts of East Antarctica, certainly the floating portions, to melt more than we ever thought before. So we're not saying that there's a big dramatic things happening in East Antarctica just yet. What we're saying is that these lakes that sometimes cause the floating portions to disintegrate quite rapidly because of rising air temperatures, they're a lot more widespread than we thought in East Antarctica. And of course, the concern we have is that if temperatures do start to rise quite rapidly, we'd expect more of these lakes to form, and we'd expect a kind of increased vulnerability of East Antarctic ice shelves. And if we remove some of those, we then start to cause that increase in outflow from the ice sheet that would cause sea level rise. So this is an area that people are working on now, and quite lots of detail, because we're worried that kind of these lakes might turn up in increased densities.
And one thing which students learn about in A-level geography is the idea of the albedo effect, and obviously how that can impact ice sheet mass, and kind of could you tell us a bit about that from a not a professional, from an expert's point of view? What is the albedo effect?
Yeah. From a glaciology standpoint, I mean, I think positive feedbacks are going to be really important when it comes to climate change. And there is one positive feedback cycle. That's a cycle where an initial change causes a reinforcement of that change, and sometimes referred to as a kind of runaway process. And one of the most applicable positive feedbacks is something called the ice albedo effect. Okay, so I think we have a slide to illustrate this. And if we were to start in the top right of that slide, let's say we have global warming in the top right there. That initial change, which might be global warming as a result of increased greenhouse gas emissions, that initial change will cause snow and ice to melt. Okay, if you melt snow and ice, you will remove a highly reflective surface that reflects most of the incoming shortwave radiation. back into the atmosphere. And all of a sudden, we're absorbing that instead. So the decrease in ice cover on the Earth or in the valley, wherever you're interested in, it works across all scales. That decreases the Earth's albedo, which is simply another technical term for reflectance. So all of a sudden then, we're absorbing more of the solar energy, we're warming the local environment and re-radiating that heat, which causes further ice melt. And that contributes to climate change and warming, which then causes more ice melt, which then decreases the ice cover, and we go in this kind of positive feedback loop that reinforces that initial change. And that ice albedo feedback works in a number of different environments. That's really important to state. It works, for example, with sea ice that forms over the Arctic Ocean. As soon as we start to reduce that sea ice extent, we start to expose a darker ocean surface, which warms up and prevents sea ice growth. It works at the scale of a valley glacier. As soon as a small valley glacier starts to decrease, it will kick in, we get darker surfaces exposed, they warm up, and they contribute to more ice melt. And it also works at the scale of the whole planet, where during an ice age, we might have 30% of the Earth's surface covered by glaciers and ice sheets, but as soon as we start to melt them, it very rapidly leads to deglaciation through this ice albedo feedback. So it's sort of a positive feedback that occurs at all scales and spatially, but also temporally as well. So it's quite straightforward in some ways, and I hope that illustration helps people understand it, but it's a really powerful positive feedback.
Brilliant. That was really clear for students to see as well. We have had a few questions come through. If there are any more questions, if you just write them in the chat on your screen. I don't know which side it is, the right hand side, which I don't know which I'm pointing to, but just write them down and we'll get through that as well. So some of the maps you showed us were obviously the imaging of Antarctica, so we could see the impact of climate change as well. And then you said also about how you can use GIS to map all the lakes, which you didn't know how many there were going to be. So students start to use GIS at school, and a lot of mine have just finished their coursework, have used a lot of GIS to map some things to do with their local area. Why is GIS an important and valuable tool in your research? And I was wondering, how do you actually get the permission almost to use it as well? So obviously it's the maps which probably go from space. So who do you have to work with to get all your data?
Yeah. Well, there's two really important things that have happened over the last few decades. One is that we've launched more and more satellites that are imaging the Earth's surface at any given time. There are so many satellites now orbiting in space, imaging the Earth's surface for all kinds of different purposes, for meteorology, for glaciology, for vegetation studies. It's fantastic. But the other big revolution that's taken place is data availability and access. That there is now a concerted effort to make all of this data available to anybody who wants to use it. So anybody watching this could easily go to, for example, the European Space Agency's website, and in a few quick steps, okay, you might need a little bit of help in one or two places, but in a few quick steps, you can start downloading and accessing imagery. I mean, Google Earth is one example. I mean, all of that is freely available imagery that people can use and they can map from. So I think the combination of just the sheer number of satellites that are now orbiting, plus this concerted effort to make sure that all of that data is freely available to anybody who wants to use it, has been fantastic for research. And GIS systems, geographic information systems, are so valuable to the research we do. I mean, if I wanted to go and measure the velocity of a glacier in Antarctica in the field, it would cost, potentially hundreds of thousands of pounds. I'd end up going to one glacier, maybe for just a few weeks or months, and that's just one glacier. I wouldn't necessarily know how representative it was of what else was going on in Antarctica. Instead, I could sit in my office here with a cup of tea, and within a few hours, you could have downloaded satellite imagery with a few little bits of software code in a GIS. I could extract the velocity of 100 glaciers within a matter of just a few hours. And there are people doing that, and without even us having to process the imagery, people are actually providing those velocity data sets. Somewhere like the National Snow and Ice Data Center in America, a great resource of freely available information that could be used. And the great thing about a GIS is that you can bring together different data sets. So you could bring together a data set of the glacier velocity with a data set of how much it's thickening or thinning. We've got satellites that can measure surface changes in Antarctica to within a few centimeters. So I could tell somebody, well, this glacier is not only accelerating, but it's also dropping in elevation. It's thinning at the same time. So, it's fantastic in a GIS that you're able to bring together different data sets, and you're able to kind of interrogate that data and look at the spatial relationships between what the different sources of information may be telling you. So it has revolutionized the way we study ice sheets over the last 20 or 30 years, the satellite imagery and the GIS systems. And, it's worth noting that there are lots of different branches of geography that now use GIS. It's a really valuable skill to pick up in your studies. It's a skill now that's becoming compulsory in most degree programs around the country. And it's also a skill that many of our graduates use in their employment as well. It's one of those transferable skills that can be taken into town planning or, road networks, or I'm just recall a fascinating job that one of our graduates was doing where they were looking at power lines and whether they might fall onto railway tracks. And it was all being done by GIS. So, it's a really important skill, and I'd really encourage students to kind of pick that up as they go along in their studies. Brilliant.
If we kind of move on to our questions before we kind of ask all guests at the end, kind of how did you get to where you are today? So there's one question, a few more have just come in as well. So one question from Finn. So it's kind of two questions in kind of one. So it says, to what extent do you think that the pandemic has impacted climate change, so reduced emissions? And do you think there'll be a significant impact? Will this be enough to impact glacial melt? So I suppose the first question is, from kind of studying climate change, you might not be, and obviously not, you'll focus on climate change in Antarctica, but do you think the pandemic has led to a reduce in emissions and therefore impacted climate change rates?
Yeah, it's not my area of expertise. I have tried to keep up to date with some of this. Some of the stories and reports during the first lockdown, at least from a UK perspective, this time last year, there was some evidence that there were kind of decreased emissions. Clearly, people weren't travelling, they weren't flying. But then more recently, I've read some kind of counter reports suggesting that actually it's been of too short a duration to really make a big difference. I think what's really useful, however, is that it's in some ways it's been a forced experiment that's allowed us to think about what life might be like where we don't travel as much, where we don't fly as much. And even those short periods where we do think there are reduced emissions, it kind of gives you a nice template or a framework to say, well, actually, this much reduced activity led to this much reduced emissions. So it's been useful, I think, to see what's possible and to see if we did kind of reduce some of the emissions, what kind of effect it might have. But at the moment, my view, or at least my reading of the literature around this, is that it hasn't had enough to offset any of the effects of climate change, unfortunately.
Yeah, brilliant. And that's actually what Finn said in the comment, because I just got them to expand and saying that actually maybe there isn't enough time, a period of time to make an impact. So you've kind of hopefully answered the same question, what you thought it might be. Another question is, before you talked about how glacial melt can impact and create more geophysical hazards. A lot of students kind of learn about the synopticity between different units as well. So could you just evaluate what risks in the future might there be from glacial melt around the world?
Yeah, from a hazard perspective, what we've seen over the last few years are, if you think of a glacier sat in a high mountain valley, it sits there and it helps stabilizes the slopes actually. And when you start to lower that glacier in the landscape, then it's almost as if the valley sides are relaxing a little bit, and so there's a debuttressing going on, and that's also aided by the fact that in these high mountain areas you might have permafrost, which is frozen, but then begins to thaw at the same time as the glaciers are melting. So we might expect to see increased risk of landslides onto glaciers or into glacial lakes. We might see glaciers that are in very precarious hanging positions breaking off, and that could lead to some kind of avalanche as well. And we can't say that any individual event, oh, well, that's because of climate change. What we're starting to see and what we think is emerging is a pattern where these events are becoming more frequent. So we know these events have happened historically. We can go back several hundred years and there'll be, anecdotal reports of these things happening. But what we think is happening and will happen in the future is that we're going to see an increased frequency of these events. Glacial lakes, particularly in the Himalaya, is something that people are really monitoring at the moment. We know that as the glaciers are retreating, the meltwater is being trapped in front of the glaciers behind some quite unstable moraine material, and it only takes those lakes to fill to a certain threshold, and then they'll burst through the moraine and we'll get the glacial lake outburst flood. And so there's a lot of research going on to try and assess the susceptibility and the vulnerability of different local populations to these lakes. And the event a few weeks ago in the Himalaya was just one example that highlighted how little we know actually about the predictability of these events. So we will see more of these events, and there's a huge amount of research effort going into predicting what might happen and when over the next few decades.
Brilliant. So that was so that was from Pete, and then we have a question from Lizzie, which I think you kind of mentioned, you touched upon, you explained a bit earlier. So in just a summary from Lizzie, would you mind saying why is the Arctic warming faster than Antarctica? So I know you gave a bit of a more complex answer before. So would you be able to give us a small anecdote, and I'll say go back and also to...
Yeah, it's a really, It's a really, really good question. And actually, I was trying to explain this to some third year geography students at Durham only yesterday, where we had a lecture on what's known as Arctic amplification. And Arctic amplification is exactly that phenomena that we've described, whereby the Arctic warms much faster than other parts of the globe, and much faster than the Antarctic as well. And we think one of the main reasons to that is actually to do with that ice albedo positive feedback over the Arctic Ocean. Because if you think of a kind of pre-industrial emissions, before we started to alter the Earth's climate, we had this seasonal expansion of sea ice over the Arctic, reflecting incoming solar radiation, keeping it cool. As we've warmed the Arctic, that sea ice is not growing to anywhere near where it used to grow to. And actually in the summer, it's really reducing in extent. And people are predicting that we might have an ice-free Arctic Ocean as soon as the 2030s, so in just 10 or 15 years. And when you remove that lid of sea ice over the Arctic, you expose this darker ocean surface, which absorbs the solar radiation, re-radiates it, prevents the sea ice growing the following year. So most of what we know about Arctic warming is related to that ice albedo feedback. There are some other more complicated feedbacks to do, for example, with clouds. Once you get rid of the once you get rid of the sea ice, you have an exposed ocean surface that's warm, it evaporates more, it creates clouds. Clouds can trap more of the long wave radiation closer to the surface. That leads to warming. There are some other feedbacks to do with black carbon, increasing the absorption of solar energy in the Arctic as well. So there's a whole number of reasons why the Arctic's warming faster, but the most important one is that ice albedo to do with the sea ice cover.
Brilliant, fantastic link to the albedo for everybody to help explain, and fantastic question, Lizzie, as well. Then Russia can have all their shipping lanes through the Arctic when that's all melted. A question from Myth, I think, saying, what is the most interesting study you've read that's also simple enough to understand for a layman? So do you have any recommendations on reading on this topic that is interesting. I can also put a link to your research as well in the chat.
Yeah, of course I'm going to say my research. No, that's a tricky one, actually. I mean, I think there are, it doesn't take long in this topic, let's say broadly glaciers and climate change. I would say there's a news story appearing on the BBC website probably once or twice a week, or maybe, once every 2 weeks. There was a well-publicised story last week that you may have seen where the Brunt ice shelf, which is very close to one of the UK research stations in Antarctica, actually broke away and this huge iceberg was released. And I would say that a good place to start would be the popular media, which these days always provide a link to the study where the research was published in what we call the peer-reviewed literature. So I would say that keep an eye on the popular media. I'm not going to tell you to go straight to the Journal of Glaciology and read X paper by Y, because that can sometimes be a little bit complicated, at least until you're studying at university and getting that support there. So I would say keep an eye out in the kind of popular news channels and the popular media. Read those articles that interest you and then click through on the link, because it will take you through to the actual research paper. And in that sense, then you can read the popular understanding in layman's terms or layperson's terms, and then you can go to the paper and read a bit more detail with that knowledge already in your head, rather than jumping straight into the papers. So, the Brunt ice shelf that broke away last week is a really good example. That example of the glacial lake outburst flood is another really good example. So keep an eye on popular media and then click through to the link to the scientific literature.
And we ask all our guests, so thank you very much everybody for asking those questions as well. So really, really interesting. I love to hear different parts and different advice as well. So we ask all our guests how did they get to where they are in their careers, and do you have any advice for students? So obviously you teach at Durham University, so you might have some advice for students picking universities, or if they're thinking about geography. But before you answer how you got there, my question is, when did you actually start learning about glaciers? Because some students do learn about it when they're in Key Stage 3, but not all students have the same education on glaciers. So before you go into it, when did you start becoming interested in glaciation?
Yeah, so I'm glad you said that, actually, because I was thinking back, and I don't think I did study glaciers at GCSE or A-level. I can't remember it if I did. I hope my teachers aren't listening. So I didn't actually start studying glaciers till I got to do my geography degree at university, and I studied them in the first year. And then I studied them, I just found them fascinating. And then I studied them in the second year, and in between my second and third year, I was an exchange student, and I actually travelled to Scandinavia to do some dissertation research. And that enabled me to see a glacier for the first time. I did a bit of travelling and I went to see a glacier, and I was completely taken in by these strange things that are, on one level, are completely inert. It's just frozen water moving. But then if you get close up to a glacier, you can tell it's moving. You can hear it. There are sounds, there's water running, there's drips, there's creaks and cracks. So on one level, they're these inert phenomena, but on another level, it's almost like they are alive, they're moving, they're dynamic. And that just completely captured my imagination. I thought, I need to learn more about these things. This is fascinating. And so in my third year, I did more modules on that topic. And then that led me into a PhD, which was fascinating. I really enjoyed learning about this subject. And then I was lucky enough to get a full-time job as an academic after that. So, I think geography, it won't be glaciology for everybody listening and watching. For some, it might be biogeography. For some, it might be what's going on in urban geography. But I think the great thing about geography as a subject is that, it's all around us, and it helps us explain our everyday experience, whether that's walking down a high street and noticing that a large number of shops are boarded up and asking the question, why is that? What is driving those changes? Or whether it's walking down a glacial valley and thinking, I wonder how far the glacier got down here. Or why does this mountain look like it does? Why does this landscape? Why have they built the road here? It just answers those everyday questions for me, and it's an incredibly relevant subject to be studying. I can't think of another subject that is more relevant to be studying, actually. So I would really encourage students to think about it as their, maybe as one of their, as their main degree program.
Brilliant. And then to think about it and go for Durham as well.
You said it, Ellie, not me.
Well, brilliant. Well, thank you so much for giving us such, so interesting and really clear, and to break this down. It was a really fantastic interview. So thank you very much for your time, and thank you everybody for joining us live as well, and those questions. And there are links. So hopefully everybody will be watching on BBC Media, BBC News, to find out some more about glaciers as well, and clicking on articles. So thank you very much, Chris, for taking your time to speak to us today.
It was a pleasure. Thank you very much.
And then I'm just going to quickly just show everybody. So it's not next week, it's got next week on the slide. It's 2 weeks' time, so 23rd of March, we are talking about Cape Town's water insecurity. So we're actually going to be joined from a professor in, I want to say Philadelphia, but I'm not sure, over the Pacific Ocean. And then we will also be Atlantic Ocean. Oh, that's my geography. And then we'll also be speaking to someone from Cape Town as well. So really, really global talk. And I know a lot of people study global water insecurity. So this will be a really fantastic talk for everybody to come and join, to talk about Cape Town's water, and particularly day zero if you studied it as well. So for me, have a lovely couple of weeks. Hopefully you get to enjoy some sun that's out today a little bit. And we'll see you in a couple of weeks.